welcome everybody. This is the 21st lecture of this course. So today we are going to talk about this new type of automaton known as push-down automaton. So what is a push-down automaton? So basically a push-down automaton is an epsilon NFA appended with a stack. So to put it in the simplest words, it is a epsilon NFA plus a stack. Okay. So what exactly does it mean? How do we define a push down automaton in the first place? Does it actually add any power over epsilon NFAs? We have seen earlier in the context of regular languages that epsilon NFAs are exactly those class of machines, are those machines which accept regular languages. Okay, you can convert any epsilon NFA to a DFA. But if I add a stack to it, does it actually add more power? Okay. So we will answer these questions in the next few lectures. But today what we want to understand is what exactly is this model, and give some examples of languages that it can accept. Okay. So once again, before I go into the model, I want to give a brief recap of what a stack is. So stack is a data structure that most of you must have seen in your data structure course. Nevertheless, let me give a brief recap. So a stack is a data structure which has it is a linear data structure, it has a linear form, and you can only access elements of a stack from one end. Okay. So usually we think of that end as the top end. So I can, if I want to add an element, I can only add it to the top of the stack, and if I want to access an element, I can only access the topmost element. If I want to remove it, I can only remove the topmost element. So in other words, if I want to, let us say, access an intermediate element, let us say some element that is contained in a cell much below, in order to access it, what I have to do is I have to pop out all the elements from the top and to be able to access it. So a stack has two operations defined on it. So it has the push operation. So push basically adds an element to the top of the stack, and pop removes the topmost element. Okay. So these are the only two actions. These are the only two actions that one can define on a stack and use to access the data structure. Okay. So this is a stack. Okay. So a few points, as I said, that so only the can be accessed at a given time, and to access an intermediate element, okay, all elements above it must be popped, okay, in other words removed. So, this is what a stack is. So, now let us see what do we mean when we say an epsilon NFA appended with a stack. Okay. So, informally, so I am just going to give the informal description today. So, a push down automaton has a input tape, a finite set of states and an unbounded stack. Okay. So, just a brief mention of this word unbounded. So, when we talk of a stack, we do not put any limit to the number of elements that it can have. In other words, the stack can store arbitrary amount of information. Okay. So, that gives that supposedly should give more power to it than an epsilon NFA. So, pictorially it would look like this. So, we have the what is called the finite control. Okay. So, this is our finite control. So, this has the states. Okay. So, it has maybe some state over here, some state here and so on, a finite number of states. There is an input tape, okay, which contains the input bits. Okay, let us call them A1, A2 up to some AN, and at any given point of the computation, the automaton is in some state, and let us say it is reading some input bit AI. Okay. So, this is essentially what an NFA or a DFA does. So, it has its input, it reads the input one bit at a time from left to right, and it is at some state. Okay. So, whenever it reads the next bit, it accordingly moves to a new state or it stays at the same state and so on. So, that is how a finite automaton behaves. Now, in addition to this structure, we have, so this is, let me just write this. So, this is the input tape. So, in addition to this structure, we have a unbounded stack, and the automaton can also access only the topmost element of that stack, but it can do whatever it wants to do with it. I mean, it can add more elements to it, or it can remove elements or do whatever, okay, but there is no bound on this stack. So, this is what a push down automaton basically looks like. Okay. So, now let us look at how the push down automaton, so how can I define an instantaneous description of the push down automaton. Okay. So, at any given point of time, the push down automaton. So, in short, this is also referred to as a PDA for push down automaton. So, it has is in some state P reads some input symbol, let us say AI, and can access the topmost element of the stack, say capital X. Okay. So, let us say this is capital X. Okay. So, these are the things that the push down automaton has access to at any given point of time. Let us say it is at some state P. Okay. So, this is the state P. It can read a input bit AI and it can access the topmost element X. Okay. So, now from this position, in the next step it can transit the state. Okay. So, it can go from P to some state Q, it goes from P to Q, and it can change the topmost element from X to some Y. Okay. So, that is how we define a push down automaton. So, it can change the top element X to Y. Okay. So, the PDA makes a at this point can move from state P to Q and can change the topmost element of the stack from X to Y. Okay. So, this is represented as, so this is so using the notation from P on reading the input symbol, let us say AI, okay, and reading the stack symbol X, the automaton goes to Q, state Q, and replaces X with Y. Okay. So, this is essentially what it means. From state P, it goes to state Q on reading AI and it replaces X with Y. Okay. So, this is what forms the basis of one step of the computation of a push down automaton. So, one more important point that I should mention at this stage is that when we talked about finite automata, there was only one alphabet. So, the alphabet from which we used the symbols of our input. Okay. So, it was called the input alphabet. But now, since we are dealing with a stack, we will allow the stack to actually have its own set of symbols. Okay. It is not necessary that the stack will have the same symbols as the input. Of course, it can have the same set of symbols as the input symbols, but we will allow it to have its own alphabet. So, which it is called the stack alphabet, and it is usually represented with capital gamma, and the symbols in the stack alphabet we will usually denote them with capital X or capital Y or capital Z or something like that. Okay. So, that is the usual convention which we will follow for our lectures. Okay. So, we allow the stack to have a different alphabet. Okay. Say usually denoted as gamma. Okay. So, formally given an input W, the PDA at any given instance does the following. It reads a bit AI from W. Okay. And now, because it is an epsilon NFA, AI can be the empty string, okay, where AI belongs to sigma epsilon. Okay. So, recall this notation that we had used earlier. So, sigma basically denotes the input alphabet, and sigma epsilon denotes the input alphabet together with the string epsilon. Okay. So, each bit AI, I should not say AI, so reads, well, so I will just say reads AI from W, and this AI can either be a sigma or it can be epsilon. goes from state, let us say P to Q, and replaces the topmost element of the stack comma x with y, where x comma y once again are symbols in gamma epsilon. Okay. So, actually we allow x and y to also take the value epsilon. Okay. So, what does it mean? So, what does it mean for x to be epsilon? Okay. So, when we have x epsilon and y, let us say some other string, okay, maybe some symbol in gamma, what does that mean? So, if we look at the description, so the description says that it replaces x with y, x is the empty string. So, it is replacing the empty string with some symbol y. Essentially what that means is that it is pushing y onto the stack. Okay. So, that is what it literally means. And similarly, what does it mean for y to be epsilon? Okay. So, once again observe that if we just look at the definition that it is replacing x with y, if y is epsilon, it just means that it is replacing x with epsilon, which is nothing. So, essentially what it is doing is it is popping out x from the stack. So, x was already there on the stack and now it is popping out x. Okay. So, this means that it is popping out x from the stack. Okay. So, basically if we have a computation like this, I mean pictorially what it would look like is, so let us say that I have my finite control, and in my finite control I have a state p somewhere, I have a state q somewhere, the machine is, the automaton is reading the ith bit, let us say ai at any point of time, and I have my stack, and on my stack I have x at the top of the stack, and let us say some string t below it. Okay, so, t is the entire string that lies below. So, what happens in the next step is, okay, so if this is the current state, what happens in the next step is from ai So, from ai the input head moves to the next symbol, that is ai plus 1. The finite state, it moves from state P to state Q, okay. And the top of the stack is replaced. So, the top of the stack which earlier had x got replaced with y, and the remainder of the stack remains the same. So, if there was some string t below it, the same string t actually remains. Okay. And as I said that it is not necessary that it actually reads a bit at every step, it can read the empty string also, the epsilon also. If that is the case, then actually the input head does not move. Okay. So, the input head stays where it is. The input head, if it is reading ai, well, it will read in the next step. Okay. So, let me give a brief view of what we are going to see in the next lecture or in the next few lectures. So, next we will see a definition of, or a formal definition of push down automata. We will look at some examples, and then we will discuss the computational power of these objects. Okay. So, if you recall at the beginning, I said that we want to study these objects from the point of view that adding this extra data structure, which is a stack, how much extra power does it add? Okay. So, that is our final goal. So, we want to understand this question: what is the computational power of these objects? Are they more powerful than finite automata? Are they equally powerful, or if they are more, what kind of extra languages do they accept? But before that, we will see the formal definition of a push down automata. What does it formally mean for a push down automata to accept an input, and then we will see some examples. So, I will stop here today. Thank you.